Artificial intelligence and quantum computing go together like a hand in a glove. And after 2 years, 87,000 users, and 5 million experiments, quantum computing is here. I'm Tanya Hall for ZDNet and Tech Republic, and joining me is Dario Gil. He is the Vice President of AI and Quantum Computing for IBM Research. Welcome, Dario.
It's a pleasure to be here with you, Tanya.
So what is your mission at IBM Research?
Well, IBM Research I like to say that it's the technical soul of the company of IBM. And our mission is simply put to invent the future of information technologies and the future of computation so that we can create new products, new services, and bring those innovations into the world. But it's to create and invent the future of information and information technology.
So what big ideas in artificial intelligence is IBM pursuing?
Well, AI, let's put a little bit on context that AI in its own right, it's a field that has been with us for many decades, right? The term itself was coined in the 1950s. In fact, there was an IBMer, Arthur Samuel, who first coined, for example, the term machine learning that is so popular today. And we've gone through many, many phases. At the beginning of it, I think the early pioneers thought that they were going to crack this problem, right? Presto, very quick, in a few summers, they were going to figure it out. And now it turned out that it was a much, much harder problem, like the idea of creating a form of intelligence that could be created by computers. And in the field, this has gone through enthusiasm and some busts. And those have been known in the past as AI winters. And what is happening is over the last 6-7 years, there's been a real renaissance in the field of AI, fundamentally driven by the convergence of three things. Machine learning, and specifically a subfield called deep learning, advances in computation power, very specifically a form of accelerators that were well suited, like GPUs, to these particular neural networks, and then the availability of data, and more concretely, labeled data that we could use to train these neural networks. The result of that is we've seen an explosion of using this form of neural network-based approach to train systems to do better language processing, better translation, better image recognition, and video processing. So I would say that we are in the narrow phase of artificial intelligence finally working. When I say narrow, what's the other bookend of the story? It would be a general form of artificial intelligence. So the kind of intelligence we humans possess, right? We're able to move from task to task, from domain to domain. We can solve problems across many, many spaces with a great deal of autonomy. So narrow today, in the far future, general form of artificial intelligence. So where we are right now is in the space in between of what we refer to and what we're working on called broad AI, which is how do we develop artificial intelligence that doesn't just address a narrow specific task, but can work across many tasks, many areas, with more interpretability. So less of a black box, with less bias, right? And more trust, more efficient and more broadly applicable to many industries.
So speaking of language processing, shed some light on the background of the AI Grand Challenge. I mean, why did IBM take on debating, and how does it work?
Yeah, so in this context that I was telling on this history of AI, there's always been a wonderful tradition of taking challenges as a way to motivate and advance the field. We saw it in the very early demonstrations of machine learning playing checkers. In the 90s, we've seen it playing chess. We saw it, a system we created to play on Jeopardy. We've seen recent demonstrations also on Go. So what we tackle on, after we finished the Jeopardy challenge, we tasked the team in IBM Research to think about what could be an exciting grand challenge that would move the field forward. And the winning proposal actually came from a researcher in our Haifa research lab. His name is Noam Slonim. And he basically proposed an idea that we should create a system that debated a human being. And what we liked about the idea, and as it evolved, was that it wasn't this black and white situation. In a game, you know whether you won or you lost. And they're self-contained universes. But we like the idea that if AI is going to manifest its full potential into the world, it's going to have to live in the world that humans live. The ambiguity of it, right? The gray areas, So arguments are wonderful in the sense that you can present a pro and a con of an argument, that depending on the context, people may be more persuaded about one type of argument versus the other. So it's a wonderfully difficult problem. And the system we've created does the following. Given a motion, let's say you're debating, we should all become vegetarians, as an example, the system has to automatically generate a 4-minute speech. So you see right away here is a big change from where we are today with most AI systems, which they have short commands, right? We may have an assistant and we give it a command and it does something in return. Now the system has to write essentially an essay and deliver it persuasively. Then the human performs their own 4-minute speech, right? Let's say they're opposed to the emotion. The system needs to be listening for 4 minutes of this long continuous speech of a human, and then extract the essence of the argument and construct a rebuttal, another 4-minute speech that is addressing the points that were raised by the human. And the human goes their own 4-minute rebuttal speech in their own right, and then there are closing arguments, which are 2 minutes apiece. So we've constructed a system that does this, that it has been created and engineered to debate, not any particular topic, but to debate in general. So to tackle this has been listening comprehension is a big deal, long continuous speech, being able to write a speech and deliver persuasively, and sort of understand how humans debate, like how do you model human dilemmas and argumentation.
Did the AI do its own initial research for the first 4 minutes of the speech?
It has to do that. So essentially, you have to give it access to a large corpus of documents. These are, millions of documents in terms of, articles that have been written and essays, Wikipedia, and so on. And from the billions of possible sentences that are out there, it has to select either what sentences or subsets of them and be able to compose a speech as a result of it. So things that the system needs to be able to do is, for example, find things and not be repetitive, right? Maybe it encounters 2 arguments, but don't put them together. Cite evidence. Sometimes the system needs to figure out who should I quote, because we all know that sometimes citing a source of authority or somebody that is respected by the audience may help with the persuasion of it. So you have to go and figure out, of all the billions of possibilities, what is the best construction of a 4-minute window that you could create? And that's a very difficult problem, right? I mean, for humans, let alone for a system that struggles, in general, computers with language, they struggle quite a bit. It's a very difficult problem. Very easy for us, very hard for the computers to do.
What will it take for artificial intelligence to earn human trust?
Yeah, that's a great question. So I would answer the question of earning trust at multiple sort of horizons. The immediate and most important task ahead of us for all of us that work in AI is that who trains this system is very important. And what do I mean by that? The contrast between traditional forms of programming and what happens in AI and machine learning today is that in a traditional program, you would encode all the rules by hand, and somebody would write all the rules for how the decision of the program is run. In a machine learning approach, you train the system by example. So then that leads to the question of what examples are you using? So let's say you're creating an AI system to assist somebody with credit scoring, or who should you assign credit to? If you go naively, say, take past history of credit decisions, and you're not careful about it, in societies or depending on where you are, you could be in a situation where the examples you're giving in the past is do not give credit to women or do not give credit to minorities and things of the sort. So that would be a terrible outcome if you just took past examples naively, train a system, automate it, and scaled it out. You would be perpetuating past biases that you want to overcome. So the trust has to do with, can I have assurances that whoever has trained these systems is trained in the right way, right? With data that is not biased, that has to go through the right safeguards, et cetera. So that would be a primary concern of where AI is today. Over time, there'll be the issues of decision making and what is the balance of decision making, how much we rely on these systems to do in automated fashion versus not.
Okay, Dario, switching to quantum computing, what types of problems can classical computers not solve, but can be solved by quantum computers?
Well, I would say the general category of problems are things where, there's a subset of problems where the number of variables and possibilities one needs to compute over grows exponentially. And typically, when things grow exponentially and they're not well mapped to the computing infrastructure that can sort of process that, you have a real problem. So let me give you an example. Let's say you want to design a new material, right? Something that has the right properties in terms of strength and, being very light and so on. If you went to perform this calculation, historically, how humans have done the engineering of new materials is experimentation, try stuff out. With the advent of computers, we say, well, let's simulate them. But the problem one has is that as you add elements that you're trying to simulate, the more electrons that these elements have and the interactions, it grows exponentially with the number of electrons. So if I have a molecule that has 50 electrons, the number of equations I need to solve is like 2 to the 50, to put it approximately, right? It's a very, very large number of equations. So after a while, I cannot compute it. So I have to approximate it. And a lot of the field in science has been about how do you approximate that. So now enter quantum computing. It turns out that with a quantum computer, because nature itself is a quantum mechanical process, if I have a machine that works like nature, meaning a machine that is quantum mechanical, I can actually simulate those processes, not with an exponential number of equations, but with a number that is approximately linear with the number of qubits I have. So if I have 50 electrons, if I had order of 50 perfect qubits, I could solve that problem. Now contrast that in the past. With a classical computer, I need an exponential. Here, I just need a linear number of qubits. So that was the original idea of Richard Feynman, that if we want to simulate nature, and that has a lot of implications for chemistry, new drugs, materials, and so on, having a quantum computer that behaves like nature could solve that problem. So that's a wonderful example of that. But there's other problems like in machine learning, in optimization, in factoring, where quantum computer could prove very, very powerful.
So, talk about the relationship between artificial intelligence and quantum computing. I mean, how does one enable the other?
Yeah, I would say the direction, what is interesting is it can go in both directions. On the one dimension is you can use AI and machine learning to better characterize quantum chips and quantum devices. So there's, because of the number of possibilities that are expressed in a quantum processor and quantum bits can be exponential. How you characterize and build a better quantum processor is very important, and AI can help us with that. Now, the other direction is also fascinating, which is, can I use the exponential states that are available to me in a quantum computer to perform classification? And we've recently published work that implements a quantum support vector machine algorithm, that there's a classical analog to it, exploiting entanglement. And entanglement is a very unique and key property that only exists in quantum computers. And we have demonstrated experimentally that the more entanglement we have, this property that is unique to quantum computers, the lower my classification error is in a quantum support vector machine algorithm. So that's pretty cool and exciting. So we have strong evidence that there are properties of a quantum computer that will help with classification tasks that are important for the world of AI. And it's just the beginning of a field, but just like we saw the impact of GPUs and AI, there's an emergent field of exploring the intersection of a new computational paradigm, quantum, and the field of AI. And there are a lot of pioneers exploring this new area, and that's what research is all about, right?
Right. Well, how will 5G wireless complement AI and quantum computing?
Well, what we're seeing is that the overall computing substrate is becoming, ubiquitous. So we see cloud, we see, on-premise systems, we see our edge devices, we see our IoT devices, and of course our phones and so on. For all of these to work in a way that maximizes the power of each one, we need good communications, right? So, fiber in some instances makes, a great deal of sense, but 5G is going to tremendously advance the power and the ability to connect edge, right, edge to edge and edge to cloud. So I think that as we make the bandwidth with which we can exchange information, the richness of the computational substrate that powers our everyday life and our businesses is only going to improve. So computation matters, bandwidth matters in communications, and data matters, right? And then, of course, on top of that is the algorithms and the AI and the applications we build. So I think that that's what it's going to enrich.
So are quantum computers solving real world problems for us today, or are they still mostly experimental machines under development?
I would say that in quantum computer, we're like in the 1950s with classical computers, right? So in classical computers, remember there were these room-sized machines. At the beginning, people had only done a few examples. Oh, this is good for calculating ballistic trajectories. And people really struggle to say, oh, what are these good for? What else are you going to do? Now, many decades later, we know the story. You can use it for everything. I think in quantum, what we've demonstrated is, for the first time, that they're real, that they work. We put a quantum computer on the cloud 2 years ago. At this point, we have almost 87,000 users who run close to 5 million experiments. So people are doing it, calculations. People have created games with quantum computers. So it's early days, but they work. And people are starting to learn how to program them, how to run little use cases around it. Now, can you do something on a quantum computer that you cannot do classically? Not yet. But that day is coming, right? So over the coming years, we will get to the point where there'll be elements that you can start doing something better than a classical, but not all things. The future of computing is going to be the blend of all of these things. We will have classical computers, we will have quantum computers working side by side.
Okay, Dario, what milestones in quantum computing do you see IBM achieving in the next year or so?
So we have been, big pioneers in this space. Over the last few years, we've built a 5, 16, 20, 50 qubit machine. So big milestones for us are to continue to grow our ecosystem, right, called Qiskit. And a lot of more people need to learn how to develop and program on it. We gotta go and deploy our 50 qubit machines for our clients, right, so that they can benefit from it and start exploring applications. And we are going to work really, really hard to continue to demonstrate advances in the machine learning space, in chemistry, and in optimization. So starting the journey of the application work and demonstrated that you can solve more and more problems with it. Ultimately, I'll tell you the grand goal. The grand goal over time, the holy grail of all of this, is to build what's called a universal, fault-tolerant quantum computer. Universal means you can run any program you want on it. And fault tolerant means you can compute indefinitely without errors. So today we have universal quantum computers, but they're not fault tolerant. They have errors. So we got to go down the road of reducing the errors and build this ultimate machine.
Well, the future of computing is very exciting. I really appreciate you shedding some light on that for us, Dario. If somebody wants to connect with you, maybe they want to find out more about your work, how can they do that?
The best way is to look under IBM Research in our website. And if you're interested in quantum, if you look at IBM Q, which is how we bring quantum computer to market, or the IBM Q experience, you get to access our quantum computers for free. You can try stuff out. There's tutorials. You can learn a great deal. It's a wonderful community there. And you can follow me on Twitter as well. It's Dario Gil A. And look forward to hearing from you.
All right. Thanks again for your time. And if you guys want to follow me and more of my interviews, you can do that right here on ZDNet or Tech Republic, or maybe find me on Twitter. I'm at Tanya Hall Radio on Twitter. And go to my website, tanyahall.net. I've got links to all my social channels. Thanks for watching.